Okay, team, it's me, Andrew Voss again, and the final force we're going to be talking about is drag, which is a little bit more complicated than the thrust and the weight. And so we're going to have a few more slides and talk a little bit longer about it. But hold on to your hats because it's going to get windy. So drag is the air resistance, and importantly, it is always opposing your direction of motion through the air. So we have a rocket moving in this upward direction. The drag force is acting against that direction of motion. So drag is the aerodynamic resistance to motion of a rocket through the air. The drag force always acts opposite to the direction of motion. The shape of the object, the rocket in this case, has a very large effect on the amount of drag produced. Bodies with a larger presented cross section, so in that case, that's how wide the rocket is, will have higher drag. So if you think about it like sticking your hand out the car window, the drag is proportional to one, how fast you're moving through the car. Like your hand's not going to feel much force at 10 miles an hour compared to at highway speeds, 60 miles an hour. And if you tilt your hand downwards like this, you're reducing the cross-section area and the drag force gets much smaller. But then in the vertical position, your drag force pushes your hand back. So certain things that jut out from the rocket can add a lot to the drag by both increasing the cross-sectional area and disturbing the flow of air around it. For model rockets, these are fins and other things that jut out that can cause a huge amount of rocket drag. On major rockets like the Falcon 9, this can be like the grid fins. They're called protuberances, and they can seriously increase the drag of the rocket by a large amount. It's also very important to shape them smoothly so that the air is not disturbed as it passes around the body. If you look at this plot on the right, you can see very smooth flow over this rounded fin geometry and a disturbed or turbulent flow around the left geometry. For reducing drag, which is very important to completing your mission at high performance, you will want to use the smoother rounded geometries so that your rocket flies more smoothly through the air and has less force counteracting its motion. And that motion, remember, is produced by the thrust. So I'll give a brief introduction here on how to calculate the aerodynamic forces. It's this equation on the right that the drag force, D, is equal to the coefficient of drag, CD, times the air density, times the velocity of the object squared, and times the cross-sectional or reference area. All of that is divided by 2. So the force from drag increases linearly with air density. So as you move up through the atmosphere in your rocket flight, the air density decreases till it's 0 in outer space. So this is reducing the drag on the rocket throughout the mission from that phenomenon alone. Now, the drag increases linearly as your area of the rocket increases. So that's how wide your rocket is most of the time. Although the length of your rocket will increase the drag from just friction on the sides of the rocket. And finally, and most importantly, the drag force increases exponentially with velocity. That means that if you double your speed or your velocity, you'll have 4 times the amount of drag. So it's very important how fast you're going to calculate the drag force. Objects moving very fast, low in the atmosphere, experience a huge amount of drag. And again, that's like sticking your hand out the car window when you're going really fast. Be careful because it might just rip your arm off. So the one thing we didn't talk about is that coefficient of drag. What is that? If we go back in this equation, it's CD. It seems like just a random thing. How would you go about calculating it? The CD is representative of the shape of the object. If we go back to those fins, this object here on the right will have substantially lower CD compared to the object on the left because of its shape and the way the air flows around it. So there's a few ways to determine what that CD is. Your options are split up between analyses and tests. So for analysis, you can use approximations from the previous testing and launch of similar shapes. You can run simple simulations online, or you can run very complex simulations using computational fluid dynamics, which is something I learned in college and we used heavily at SpaceX. But some of these CFD simulations could use many computers at the same time, computing results for weeks on end. So they are very intense from a mathematical perspective, but they give you the best analytical estimates of what these drag coefficients will be for different phases of rocket flight. Now on the test option, you have more options. And we do these things as well with model rocketry and at SpaceX. So the wind tunnel test flows air over a rocket at different speeds and velocities and measures the force acting on the rocket. You can also do a flight test without even knowing your coefficient of drag yet and analyze how high and fast your rocket went during flight, and then back out the coefficient of drag based on what your thrust was and what your weight was, which are much more easy quantities to measure. So I'll leave you with some thoughtful questions for the end of the drag session. When is the drag on the rocket the most in a rocket flight? How can you go about reducing the drag of the rocket? How could you determine when the rocket will reach the speed of sound? And why does that change the drag? When is the rocket most likely to break from the forces on it? See what you can figure out and maybe do some research. Thanks.